Everyone assumes electric vehicles will eventually power the grid. After all, they're batteries on wheels connected every day. This episode explains why that intuition is wrong, at least at the beginning. The problem isn't technology, it's coordination. Before EVs can become grid infrastructure, something else has to exist first, a system that can coordinate assets with certainty, not hope. This video is about the layer almost everyone skips, the coordination layer that determines whether EV participation is possible at all. The logic behind EVs powering the grid feels bulletproof. Millions of vehicles, large batteries, daily grid connection, multiply those numbers, and you get something that looks like transformational capacity. And that's exactly why this idea is so persuasive. But history is full of ideas that worked perfectly on paper and failed in practice. What looks obvious often hides the hardest problems, especially when humans, ownership, and behavior are involved. That's where this story starts to break. An EV virtual power plant is a simple idea. Vehicles charge when energy is abundant and cheap. They act collectively, aggregated by software into a single resource. And during peak demand, they discharge energy back to the grid. In theory, personal vehicles become grid infrastructure. That's the promise. But the difference between a theory and a system is reliability. And reliability doesn't come from batteries alone. It comes from control, predictability, and consent. That's where the complexity begins. The numbers are undeniably seductive. Hundreds of millions of EVs globally, large average battery sizes, total theoretical capacity rivaling national grids. On paper, it looks like the answer is already here. But VPPs don't run on potential. They run on assets that show up when called, behave consistently, and respond without negotiation. The grid doesn't operate on averages, it operates on certainty, and this is where the math stops being enough. Virtual power plants require three things. First, control, not requests, but command authority. Second, predictability, behavior operators can depend on. Third, consent, agreement that doesn't disappear under stress. EVs reliably provide none of these at scale. Not because the technology is immature, but because ownership and human behavior introduce uncertainty that grids cannot tolerate. This isn't an engineering gap, it's a structural one. EVs fail on control because they belong to people, not operators. No grid can assume command authority over personal vehicles. They fail on predictability because human schedules are noisy, departure times change, charge levels fluctuate, life intervenes. They fail on consent because people tolerate background optimization, but they don't tolerate feeling constrained. The moment participation threatens mobility, engagement collapses. These are not bugs, they're features of personal assets. Here's the Feynman simplification. You can schedule a machine, you cannot schedule a life. Grids require precision. Human behavior produces variance. The moment you try to coordinate millions of personal decisions at grid scale, predictability collapses. This isn't a moral statement, it's a systems constraint. And ignoring it doesn't make it go away, it just delays failure. The grid doesn't need more batteries, it needs dispatchable certainty, assets that respond with near-perfect reliability when called. No exceptions, no surprises, no human friction. This isn't about energy capacity, it's about operational trust. Without certainty, even massive storage becomes noise, not infrastructure. And this requirement quietly disqualifies EVs as the starting point. Stationary assets solve the coordination problem first. They don't move, so availability is predictable. They don't surprise you. Behavior is deterministic. They don't argue back. Software commands, hardware obeys. They sit, they respond, they dispatch. Stationary batteries create the coordination layer the grid needs before adding the complexity of human behavior. This sequencing is not optional. Everyone jumps straight to EVs because the batteries are big, but they skip the hardest part, building a system that coordinates millions of assets without human attention. First, stationary assets prove reliability. Then, software learns orchestration. Then incentives align behavior predictably. Only after that can EVs be absorbed safely and quietly. Skipping this order guarantees failure. The sequence always looks like this. First, stationary assets prove dispatch at scale. Second, coordination infrastructure matures. Third, EVs participate through managed charging. Only then does vehicle-to-grid become viable. When EVs finally join, they don't change the system. They're absorbed by it. This isn't a prediction. It's structural necessity. For founders, the opportunity isn't EV integration. It's coordination software. For investors, capital flowing into EV-first VPPs is premature. The winners build platforms before consumers. For operators, reliability must be proven with controllable assets before adding behavioral complexity. Rushing to EVs risks both technical failure and public backlash. The order matters. There is a specific coordination architecture that makes EV participation inevitable and safe. But if you try to start with EVs, you'll never reach it. That architecture is the real bottleneck. And it's not something you explain in a single video. Coordination isn't just software. It's technology, market design, regulation, and behavioral economics intersecting. Getting this wrong doesn't just delay progress, it poisons future attempts. This is where we stop. Most energy debates fixate on hardware. The real battle is coordination, where technology, incentives, regulation, behavior, and grid stability intersect. This is where dispatchable certainty is created or destroyed. And this is where value quietly accumulates long before consensus forms. The companies that understand this layer will define how EVs eventually participate, not the other way around. TaBIS focuses on the coordination problems that determine which technologies win, which business models survive, and where capital creates real value, not narratives. This isn't about predicting the future. It's about understanding the constraints that shape it. See you next time.